Okay, I think it's recording now. Okay, so today's going to be more of a proof type situation, where I'm going to prove that if you throw a projectile, it will always trace the path of a parabola, given a few assumptions. So, first assumption number 1, no air resistance. Assumption number 2, local gravity is the same everywhere. Wait, I've got tissue. Wait. Okay, I'm back with the tissue. I'm back with way to rub out the chalk. So just to recap, we decided that there's no air resistance to mess up the calculations, and that local gravity is going to be the same everywhere. Now let's think about this real quick. So, one of Newton's laws, I've forgotten which one, states that if you have an object moving, imagine this is a ball. Yeah, if you have an object moving, then it will continue moving in a straight line at the same velocity, assuming no force is acting upon it. So, let's think about it. So you throw the projectile, it's moving, but then, so this is going to be the arc projectile follows. So it's moving, and then everywhere on this point, gravity is going to be pulling it down. And the rate at which gravity is pulling it down, in other words, the acceleration of gravity at that point, we are going to call g. Right, that's going to be the acceleration of gravity. So on Earth, that would be 9.8 meters per second squared. On Jupiter, I think it would be about 15 meters per second squared. On the Moon, it's about 1.6 meters per second squared, I think. So yeah, there's a few ways. There's a few different values we can put for it. That's why we're calling it g. Now let's think about this. So if the only force acting upon it is local gravity, and the only acceleration it will be feeling is that of gravity, and we want to know distance. So distance I'll call x. Velocity I'll call v, and acceleration I'll call a. Right. Now, what can we say about x, v, and a? Well, we know that d over dx is velocity, and d over dv is acceleration, right? So, if we have the derivative of the derivative, so we have d over d, then we know that velocity is the d over dx. Right, so we have a derivative of a derivative, so that's just going to be the second derivative. That's just going to be we are no position. We know that second derivative is just going to be equal to that constant g. Right? Well, now we have a pretty simple differential equation to solve. We can just integrate it twice, and we'll get the answer. So we know that d over dx must equal, I'm going to put a negative here, because gravity is going to be accelerating you downwards instead of upwards. So d over dx is going to be, we integrate that, so then we get negative x times g, then plus a constant, and because we know, and then because of this circumstance, that constant is going to be our initial velocity. Now we can integrate that, so I'm going to get rid of this top bit. Now if we integrate that to just get x on its own, and I'm going to call it f of x. So it's just going to be the function of where x is. the function of the locus of all the points where x is. Right? So then we just need to integrate this again. So we have negative x squared on 2. Negative g times x squared on 2 plus x times the velocity. Then we have another constant, which, because of this scenario, is actually going to be our altitude. Right? And that's it. We know the function for our position is an order 2 polynomial, which is quadratic. And even better, it's an order 2 polynomial, which assuming gravity is constant, which in most cases gravity is pretty constant, then is a positive constant, sorry. Then this is going to be negative quadratic. So that makes sense, because if I were to plot it, let's say altitude is 1, velocity is whatever, then because as a negative x squared term, they don't have one hump like that, which does make sense. So yeah, this is my proof that if you throw an object, the path it'll take will always be a quadratic. See you next time.